Today we're going to talk about star cycles and our sun. Here's our objectives. Make sure you read through those. It's going to help you focus. Make sure you have your note guide out and you're ready to write down your notes. Or alternatively, you've pulled up the e copy so that you are ready to type out your notes, as the case may be. So, this is where we left off with the last one when we were talking about nuclear hypothesis that a protostar becomes a star once it hits 15,260 degrees Kelvin. Nuclear fusion begins, and we get the star. And there's our star. And we said that we hadn't talked about some of this stuff yet, and that the stuff was going to come back up, and we are ready for our stuff now. Okay, so moving forward. Kelvin. Kelvin is a scientific measure of a temperature. It's most closely related to Celsius, as we can see when we look at this chart here. Make sure you know that 0 Kelvin is absolute zero. This is no movement of atoms. We see this in space. We can do this momentarily on Earth in very specific conditions, but it's really hard to recreate on Earth. Notice that 273 degrees Kelvin is 0 degrees Celsius, which is the freezing point of water. So it's different enough that it's kind of awkward to use on Earth, but we use it when we talk about temperatures in space mostly. Nuclear fusion. It's a process where we take two things, two nuclei, and we combine them to make a heavier element. So initially, the young stars start with hydrogen and fuse them together to make helium. So we get a new element. This is the only way we get new elements naturally. Stars doing this, or we get the explosion of stars, as we saw in our video on the Big Bang. Once the star is ignited, it is a main sequence star. So our sun is currently a main sequence star. Main sequence stars are fusing hydrogen to form helium, and that's the energy that we are seeing from the sun. It takes about 10 billion years to consume all the hydrogen in a main sequence star. So our sun is about halfway through its life cycle as a main sequence star. So it's a balancing act as to whether it stays the step it's in or whether it moves on to the next step. And to know what this means, we should also know a little bit about the star. So make sure you draw this out. You have this picture or a similar picture on your note guide, so go ahead and label this. You have the core, the radiation or the radiative zone. It depends on what book you're looking at. Convection zone or convective zone. That should be a V there, not a D. I will change that shortly. So the core is where the heat is generated. The radiative zone is where it's starting to move out. And the convection zone is where the heat is circulating. So we have the energy pushing out. We have gravity trying to push down. These are the forces that are the balancing act. So as long as the nuclear reactions are taking place, the internal force, the energy, is going out, and the external force, the gravity, is pushing in. So those are our balance forces. But at some point, we're going to run out of fuel, right? There's only so much hydrogen that was in the star to start with. So once the hydrogen is consumed, fusion stops. And now we move on to the next step. So this is what's moving on, what's causing the next step to happen is we run out of fuel. Hydrogen is gone. So here we have the main sequence star, and then we're going to move on to the red giant. So the layers collapse. So the outside, the conductive and the radiative zones collapse. This is going to cause that domino effect again. The outer layers are going to collapse in. We're going to get a fusion of helium to carbon. So we have the two helium atoms colliding, and they are going to make carbon. Now the forces are going to regain balance. We now have a new fusion taking place. The fusion is going to push up. The gravity is going to push down. In the meantime, the outer shell of the star expands a lot, 10 to 100 times larger than our sun currently is. Think about what that's going to mean for our planet. We're going to come back to that. Red giants are going to last about 100 million years. Not billions, but millions, okay? So, big difference in the length of this step. Okay, so then for our star, there's not going to be enough pressure for the next step. So it runs out of fuel again, and now we have a bunch of carbon, and it all comes down, but there's not enough to start the next fusion. Carbon's just sitting there. The core is now very dense. How dense is it? It's so dense that a tablespoon, so you can put a tablespoon in your hand, a tablespoon would weigh 5 tons. That's the weight of an elephant. Oh, think about that, trying to hold the weight of an elephant in your hand. And then the outer layers now drift away because there's not anything to hold it in, right? There's not fusion going on. So then we get a planetary nebula. So we get something that looks like this. We have the white dwarf at the very middle, and then we have the nebula, remember, just a cloud in space, and it's drifting away. Now the white dwarf is the brightest color, is white. So it's the brightest visible spectrum, and it's going to fade from white to blue to red, and eventually black, meaning no light. And the black dwarf will still have gravity. It didn't go anywhere. We still have tons of material there. But we can't see it anymore because there's no energy left. So, in summary, stars like our sun, which start as a main sequence star, will eventually become a red giant. Ours has about another 5 billion years before it becomes a red giant. Then it'll become a planetary nebula with some type of cloud, interstellar cloud. Eventually, that cloud dissipates, and you end up with just the white dwarf. The white dwarf goes through the different colors, and then eventually ends as the black dwarf, which you can't actually see. You just put it there, so you can kind of get the idea that it's there. You should watch this. It'll give you a full idea of what will happen to Earth when it dies. And that is the end of today's lesson. I will talk to you soon.